from the coffee break. Welcome to the first session in this afternoon. It's the fault-resistant one session, and we will have two talks. The first one will be a live presentation. Second one will be pre-recorded, and we have the questions afterwards. You probably already know the procedure. We have two microphones in the aisle, and if you have questions, please step up to the microphones and then ask them. So the first talk will be given by Simon Tolek, and it's called Fault-Resistant Partitioning of Secure CPUs for System Co-Verification Against Faults. So the stage is yours.
Okay, hello everybody, thanks for coming. So thanks for the introduction. I'm going to present the work entitled Fault-Resistant Partitioning of Secure CPU for System Co-Verification Against Fault. This work has been done in collaboration with the Technical University of Graz and involves all the people mentioned here. So let's start with the introduction. To set the scope of this presentation, we focus on fault injection attacks injected in a system composed of a processor executing a software program. So fault injection attacks consist in applying abnormal physical stress to an embedded system, such as high temperature or electromagnetic radiation. Such an attack is illustrated on the picture on the right, where you can see the electromagnetic probe targeting the chip. So these physical attacks induce computational errors in the system, leading to an undesired behavior of this one. From a security point of view, this can be used by an attacker to create vulnerabilities in the system, such as the ability for an attacker to retrieve sensitive data like a cryptographic key or to acquire execution privilege on the platform. Consequently, studying fault injections to better understand their effect is useful to develop methodologies to analyze system security or to develop countermeasures. So before going into our contribution, it's important to understand the typical anatomy of a fault injection attacks on processor. So on this figure, you can see the different abstraction levels involved in the attack. So at the bottom of the figure is a hardware layer where a physical stress in the microelectronics leads to incorrect values in the circuits, such as bit flip, bit set, or bit reset. And then this faulty value propagates through the microarchitecture. At the software layer, so faults in the underlying hardware lead to an unexpected behavior of the software, and this effect can be modeled either at the binary level, such as instruction skip, branch inversion, or at the source code level with control flow or data corruption. So to understand the effect of fault, experimental characterization is a valuable technique. The approach is often black box as the evaluator do not have access to processor implementation. They apply a physical stress to the chip and directly observe the consequences on the running software. However, some works have reported unexplainable fault effects at the software level using this black box approach. Consequently, we need to open the box and look at how it works. More recently, other works have highlighted the importance of considering microarchitectural mechanisms such as pipelining, prefetching, forwarding, or the memory cache, since this mechanism can highly influence the final effect of fault on the software. So consequently, in addition to experimental characterization, pre-silicon analysis are useful techniques to detect bugs and vulnerabilities in the early stage of development of the chip. And since we're interested in security, the approach must also be exhaustive. So in the literature, pre-silicon evaluations often relies on simulation or formal methods. So on the one hand, simulation executes concrete instances of the system and is an efficient bug-finding tool, but corner case vulnerabilities are hard to spot. On the other hand, formal methods reason on a system model to prove properties, often considering symbolic execution traces. Well, as visible on the figure, related work are split between hardware and software domain. So hardware methods hardware methods have been mostly driven by research in cryptography. So tools like Fiverr, SynFi, or firmware that will be presented in the next talk evaluate a fault-free and a faulted circuit. So they compare these two circuits to determine whether a fault can trigger an incorrect circuit behavior. Performance-wise, a tool like Fiverr can evaluate AES with one fault in 22 seconds or with two faults in 130 hours. So, however, these tools are not suited to model program execution with faults. On the software side, so software methods focus on program evaluation. Tools like LISA or BinSec directly model the effect of fault at the ASL level with fault like instruction skip. And performance-wise, BinSec can evaluate a bootloader with one fault or a simple pin comparison program with up to 10 faults in a few seconds. So it is much more efficient, but this approach ignores from the underlying processor implementation, and as we discussed before, they ignore subtle effects due to the microarchitecture. Finally, there are combined effects that consider both hardware and software. Most of these approaches have been first proposed in the safety context, relying on simulation techniques, and more recently, tools like Simplify or Macroarchify have been proposed in security context. So the main advantage of this tool is to identify vulnerabilities resulting from a complex interplay between hardware and software, something which is impossible using hardware-only or software-only methods. However, since we consider both hardware and software, this approach encounters scalability issues, and typically Macroarchify can only evaluate 100 instructions on a small in-order CPU with one fault in a few hours. So in a nutshell, this introduction has emphasized that hardware or software-only techniques are insufficient to understand the full potential of fault injection on the software. So we need combined hardware and software analysis, which provides security guarantees, which is exhaustive using techniques like formal methods. I said exhaustive techniques, so this requires exploring the entire state space, which may lead to scalability issue, and this limitation is even more visible when considering combined approaches. So our work in this context proposes a methodology decomposing the monolithic hardware-software co-verification into two steps to contain the state space explosion. So using our methodology, we can address previously intractable use cases. So the remainder of this presentation is divided as follows. So I will then describe the methodology we propose to evaluate system security. I will compare our approach against existing work to validate the methodology. Finally, I will present the OpenTitan security evaluation before concluding this presentation. So let's continue with the methodology. So our methodology exploits the fact that security critical systems often implement hardware protections. So based on this assumption, we perform a preliminary evaluation of hardware security, and this hardware evaluation is run only once, and remaining faults not detected by the hardware that are potentially harmful for the system are then evaluated in a second step with different pieces of software. So you can see the high-level view of the methodology of the workflow on the right, which takes as input a hardware design, a binary program, and an attacker model, and as an output, determines whether an attacker can reach vulnerabilities in these hardware-software systems. The top-level box is a hardware evaluation, and the bottom box uses the reduced fault model produced by the first step to evaluate software with faults. So, to split this verification into two steps, we require strong guarantees from the hardware. We need to be sure that ineffective fault as a hardware cannot be used, cannot have effect on the software. So, however, as mentioned in related work, existing hardware techniques often relies on bounded model checking and compare a fault-free and a faulted circuit. Consequently, they only provide bounded guarantee, and unfortunately, they scale only for a few clock cycles. So a few clock cycles is insufficient to ensure that faults now have a long-term effect when evaluating program of hundreds or thousands of instructions. Consequently, we need unbounded guarantees from the hardware about security. The kind of protection we consider are referred to as concurrent error detection scheme, and as visible on the figure on the right, they consist of a target function that produces a main output of the circuit, primary output of the circuit, a prediction function that independently generates some predicted characteristic of the output, and a checker that compares the output with the predicted characteristics and raises an alert on a mismatch. The operation of the prediction function and the checker can be delayed of some clock cycle to increase the practical difficulty of attacking the circuit. So this countermeasure includes spatial redundancy, like duplication or triplication, informal redundancy, like error detection codes. We formalize the security of this protection with the notion of K-fault security as follows. So assuming at most K-fault are injected in the circuit, we have the guarantee that the circuit output are correct, or an alert is raised as most D clock cycle after the incorrect output have been produced. So to prove K-fault security with unbounded guarantee, we introduce the concept of fault-resistant partitioning, which is the cornerstone of our contribution. So let's consider the circuit on the right. So you have logic gates, including registers and combinational gates. Now, let's assume partitioning of circuit register with color boxes. I assume that I have a budget of K fault. So K1 fault are injected in the partition. So this means that I can corrupt the state of one or several of these partitions. And I have K2 faults that are injected in the remaining combinational logic. Finally, I also assume that the alert signal is never triggered. So this partitioning with the color boxes is a K-fault resistant if I have the guarantee that there is at most K1 plus K2 faulty partition at the next clock cycle, and if there is no corrected output. So the intuition behind this is that I allow fault to occur in partitions, but the fault cannot propagate to other partitions or to the outputs without triggering the alert. Our work also provides a theorem that K-fault resistant partitioning implies K-fault security. Consequently, proving K-fault security proving K-fault resistant partitioning instead of K-fault security has the advantage of not needing to enroll the circuit, since fault propagation is abstracted, and this provides unbounded guarantees. However, the converse of the theorem does not hold, so it's only a sufficient condition, and it over-approximates K-fault security. So some circuits are consequently K-fault secure, but we cannot prove it using this technique. So in a nutshell, the implementation we propose to build this K-fault partitioning, so as visible on the figure, takes as input the hardware design and the fault model. So the algorithm has two steps. So first, the build partitioning procedure merges partition as long as the fault can propagate from one partition to another. And once we reach a fixed point, we evaluate whether the identified partitioning can guarantee output security, output integrity. And the result of this algorithm are exploitable fault location that are potentially harmful for the system and not protected by hardware countermeasure. So the implementation relies on Cadical SAT solver, is open source, and has been rewarded with a CHES reproducibility badge. So for a second step, for co-verification, as you can see on the workflow, it takes as input the hardware and now the software also, with faults and in particular as the exploitable faults identified during the first step. So it is the implementation is based on the very lighter environment provided by the OpenTitan project, which is a use case we'll evaluate later. And as visible on the figure, the simulator controller exhaustively simulates every possible faults not captured by software to determine whether they can be leveraged in an attack. So let's now validate the first step of our approach on impeccable circuit. So we choose to work with impeccable circuit as no similar works exist on CPU for comparison. So this allows us to compare against previous work like Fiverr, to evaluate our performance, and also to consider hardware robust against multiple fault attacks. So in a nutshell, what is impeccable circuits? So these are symmetric block cipher protected with error detection codes. And they are designed to detect up to 3 faults, and the protection have been extended to 7 faults for AES. And when the countermeasure detects a fault, an error signal is raised and output are zeroed out. So we evaluate Skinny and IS block cipher. So with 2 faults, we prove the robustness of Skinny in 10 seconds and IS in 4 hours, whereas the state of the art, the author of Fiverr, reported 130 hours. With 3 faults, our approach first failed to prove the security. Investigating the counterexample revealed some exploitable fault in the checker mechanism. And finally, assuming that I do not inject fault in this checker mechanism, I can prove the 3-fault security of Skinny in 40 seconds and AES in 55 hours, a result that has never been obtained before with the state of the art. So let's now evaluate OpenTitan. So OpenTitan secure element is, to our knowledge, the only open source software hardware systems that is protecting against fault. The CPU used in the platform is the Secure IBEX, which implement protection against fault like the dual core log step that instantiates the IBEX core twice and they operate with a delay of 2 clock cycles. And the shared register file between those 2 cores also implement protection, like error detection codes that protect the data, and also glitch detection that protects the control logic. We consider the following an attacker that can inject a single bit flip anywhere at any time during processor operation. So first, about hardware evaluation. So our algorithm builds the partitioning you can see on the figure on the left. So this builds the main core, the shadow core, and other partition in the register file or elsewhere in the microarchitecture. So a fault in this partition cannot propagate to other partition or to the output without being detected, except for 172 exploitable faults we find in the register file. Performance-wise, it took 26 hours to build and prove the partitioning of the dual core log step. About the register file, we found this exploitable fault in 1 minute and 30 seconds. And we also consider a restricted fault model only targeting the data stored in the register file to check whether the error detection code protection works, and we prove its robustness in 12 minutes. Finally, to evaluate the full IBEX security, against one fault, we use this individual partition, this partitioning identified for individual modules. And assuming that no faults are injected in the register file, we can finally prove its one-fault security in 42 hours. So to summarize, every single bit flips are captured in the secure IBEX except those in the register file, and we are going to see in the next slide how they can be leveraged in an attack on the software. So first, we consider the first stage of the secure boot that is provided by the OpenTitan project, and we consider an attacker that want to bypass the memory signature check. We use a violator-based framework presented before, and our approach proves the robustness against one fault of this piece of software. The faults in the register file are either not powerful enough to bypass the memory comparison, the signature check, or can be captured by software protection implemented in the software. We also evaluated 2 other pieces of software, such as Verified Pin and TinyAES. So they are not provided by the project, but we ported them to a platform, and we consider an attacker that want to either bypass the pin comparison or to meet requirement for differential fault analysis on AES. So our analysis revealed that this software are insecure, and we find successful fault attacks. So just a few words about the vulnerability in the register file. So the exploitable faults allow an attacker to read data from incorrect location. We reported the vulnerability to Open Python project, and we proposed a security fix that we proved, and our fix was integrated into the project. Consequently, the security box we evaluate is now proven one fault secure unconditionally of the secure of the evaluated software. So let's conclude this presentation now. So we introduced a two-step methodology that reduces the complexity of hardware-software co-verification. The first step is a preliminary analysis of hardware countermeasures, and remaining faults not detected by the hardware and that are potentially harmful for the system are evaluated in the second step with different pieces of software. The notion of fault-resistant partitioning provides unbounded security guarantees, which is crucial for software co-verification. It outperforms state-of-the-art solver like Fiverr. It is also competitive with firmware that will be presented in the next talk, but we provide unbounded security guarantees, and we are the first work to evaluate AES against free fault. When introducing the software in the second step on processor system, we can address previously intractable use cases of thousands of instructions, such as the secure boot of OpenTitan. Thanks for your attention. Do you have questions?
Okay, let's thank the speaker again. Do we have any questions from the audience? If you have any, please step up for the microphone and you can directly ask your questions to the speaker.
Hello, thank you for your presentation. So during your identification phase, you found out that some faults are exploitable. Would you elaborate? How do you define exploitability on the register file, for example, for the OpenTitan?
Yeah, of course. So exploitability just means that the notion we introduced about fault-resistant partitioning cannot prove that this fault is resistant. But as mentioned, to provide unbounded guarantee, this property is another approximation of the real security of the system. So we don't know if these are real vulnerabilities or if it's just a false positive. So that's why we have to evaluate in a second step with the software if these faults can be exploited. And it also really depends on the piece of software we evaluate. So we know they are maybe not protected, but we have to evaluate if they can be used in an attack. That's what I define by exploitable fault.
Okay, and the second question is that during your verification phase, by any means, do you consider optimizations that are as the result of synthesis tools on the gate level, netlist, and stuff like that?
So that's a good question. So we take as input a hardware design, and if we start from the RTL, you're right, the synthesizer can optimize protection. So that's why it could be interesting to start directly from the netlist. So here we only consider logical netlist, not a technological netlist. Mm-hmm. But if you start from the RTL, you're right, you have to know that you may fail to prove the security because the compiler, the synthesizer, introduce some optimization that remove away the protection.
Okay, and the last question, have you done any post-silicon to compare your proofs versus the actual silicon? Or
I did not carry out any experiments with a post-silicon netlist.
Okay, thanks.
Okay, are there any other questions?
Thank you very much for the talk. I just want to ask, so you present some results with 1-bit faults on the CPU. Have you tried other fault model?
So since we are working at the netlist level, so everything is modeled at the bit level. So the combinational gates are bit level gates. And the bit flip fault model encompasses every other fault model like fault reset, fault set, because you know if you apply a bit reset on a 0, it has just no effect. And if it's a 1, it is akin to a bit flip.
I was thinking, for example, about like two-bit flips, for example.
So the processor we evaluate is not robust against 2-bit flips.
Okay.
So of course we cannot prove its security, and we have to evaluate with in the software step every possible single bit flip, since we cannot prove anything from the hardware step. But that's why we also validate our approach on a cryptographic circuit like AES. So it is, I'm not going the good way, but so we evaluate AES and Skinny, so some block cipher with up to 3 faults to ensure that our methodology is also valid with multiple fault attacks.
Thank you.
Okay, so then I think at that point time is over. So let's thank the speaker again. And now we are going to have the second presentation, which is a pre-recorded video, as far as I know.
Before I introduce the method, first,
Okay, so yeah, the
thanks
second talk is called set-based formal verification of fault injection countermeasures for cryptographic circuits, and the talk is recorded and will be given by Hyewon Tan. Hopefully, pronounced it as close as possible. So yeah, please listen to the talk, and then we will have a round of questions afterwards.
Thanks for the invitation. My name is Tan Huiyu. I'm a Master of Science graduate from Shanghai Tech University and now working in Wisdom Technology. Our collaborators include Shanghai Tech University, Wisdom Technology, Chinese Academy of Science, Birkbeck University of London. Today, I will be presenting our work, set-based formal verification of fault injection countermeasures for cryptographic circuit. First, I will introduce the background. Fault injection attack is an active physical attack in which external factors are introduced during the encryption or decryption process, causing errors in some of the operations. This error can lead to the leakage of information related to the cryptographic key. Fault injection can be categorized into several types. From the perspective of fault injection mechanism, it can be divided into clock glitch, voltage glitch, electromagnetic pulse, and laser beam attacks, among others. Based on the duration of the fault, these attacks can further be classified into transist, persist, and permanent. The application scenarios for fault injection attack, including bypassing security mechanism, generating incorrect plaintext, ciphertext, or signature, and combining with other techniques such as side-channel attack. Here is an example. This circuit has 4 inputs A, B, C, D, and an output P6. When given the input as 1, 0, 0, 0, the output of each gate from P1 to P6 is 1, 1, 1, 1, 0, and 1. Then we inject fault at gate P3 with reset or bit flap. Its output turns to 0 and finally propagates to P6. Then the output of the circuit changes to 0. The countermeasure against fault injection attack can be categorized into physical level and digital logic level. Physical countermeasures including introduce randomness to increase the difficulty of controlling fault duration, clock packaging protection and glitch detection to raise the difficulty of fault injection and so on. Digital logic countermeasures usually using different redundancy, such as spatial redundancy, temporal redundancy, and information redundancy, and so on. However, how can we ensure the fault resistance in cryptographic circuits? Common verification methods can be categorized into the following types: physical test, simulation-based verification, and BDD-based verification. But there are many problems with those tests. Physical tests are always limited by known attack methods and equipment. It also has the low efficiency with high cost. Simulation-based verification also limited by test cases and fault injection vectors, so it sometimes has a low coverage. The most important is that those two verifications cannot guarantee the security. BDD-based verification can cover all test cases and fault vectors. It also has a theoretical guarantee that verification success implies security, but it is still facing the challenge of combinational explosion, high computational complexity, and low verification efficiency. Inspired by equivalence checking, our work proposed a set-based verification method. Before I introduce the method, first I will give the circuit model. A K-clock synchronous sequential circuit SK is defined as a tuple I, O, R, S0, and C, where I and O are the set of primary input and output. Flag is the output flag of checkpoint, where flag equals to 1 means that a fault has been detected. S0 is the initial value of register, and R is the set of the register. C is the set of the combinational circuit. Next, I will introduce the fault type, fault event, and fault vector. Fault type determines the type of fault represented as T, where set changes the output of gate to 1, reset changes the output to 0, and bit flaps the output of gate from 1 to 0 or 0 to 1. Fault event denoted by E, sigma, beta, tau, where sigma specifies the clock cycle of the fault injection, beta specifies the gate on which the fault is injected, and tau specifies the fault type of the fault injection. A fault vector represents a set of fault events and also defines all the faults used by adversary. Persistent and permanent faults can be described as a set of fault events, where a fault tau is injected into gate beta and lasts for a continuous series of clock cycles. Next, I will give the fault resistant model. The capability of the adversary is given by fault resistance model zeta, where NE is the maximum number of fault events per clock cycle. NC is the maximum number of clock cycles in which fault events can occur. T specifies the allowed fault type, including set, reset, and bit flap. L defines the vulnerable gates, including C, R, and CR, where C for the logic gates in combinational circuits, R for memory gates, and CR for both logic and memory gates. The fault resistance model describes the set of all possible fault vectors zeta that an adversary may use. After that, we then give the fault resistance verification problem. The circuit S is fault resistant against model zeta under blacklist B if and only if all the fault vectors V belongs to zeta are ineffective. Ineffective means that the fault in fault vector V is not change the output of the circuit or the error flag is set in time. We also provide the complexity of fault resistance verification problem. We give that the problem of determining whether a circuit S' is fault resistant is co-NP complete. That means the problem of determining whether a circuit S prime is not fault resistant is NP complete. So what we need to do is to prove this problem is NP complete, and finally we can get that problem is co-NP complete. And so if we want to prove that this problem is NP complete, we first need to prove this problem is NP. To show the problem is NP, we first non-deterministically guess a sequence of primary inputs and a fault vector, then construct the fault circuit S prime in polynomial time by traversing and manipulating gates in the circuit, and finally check if the sequence of primary outputs S and S prime differ at some clock cycle before the error flag output differ in polynomial time. The NP hardness is shown by reducing from the set problem. The combinational circuit can represent a Boolean formula phi, where the inputs of circuit are the Boolean variables of phi, and the output indicates the result of phi. C1 includes 2 times NE plus 1 C phi with the same input. The output of Ci is stored in register Ri. The error flag is 0 when it doesn't detect the fault. This set problem phi is satisfiable if and only if the circuit is not fault resistant under model zeta. Here is an example. As shown in the formula, if there are no faults, then phi is unsatisfiable. When inject fault on circuit, if the circuit detects the fault in time, then phi is also unsatisfiable. But if it cannot detect the fault, then phi is satisfiable. Then I will introduce the set-based formal verification approach. First, I will introduce how to encode the fault. For each gate, we give it a control input C to determine whether it will inject fault. For example, for the unary operator, when C is equal to 0, the gate beta operation as 0, but when C is 1, the gate do the faulty operation. Then we extend it to encode multi-fault. For each gate, we provide signal B to control fault type. For example, for a binary operator, if we want to inject set, reset, or bit flap selectively, or we want to inject no fault, then we can provide it 3 signals, B1, B2, and B3, and controlled input C. When B1 equals to B2 equals to 1, then we select the fault set. When B1 is 1 and B2 is 0, then select the fault reset. And when B1 is 0, then select the fault bit flap. Also, if the C is equal to 0, that means we do not select any faults. Use such a encode method, we then construct a conditionally controlled faulty circuit, giving a circuit S, a blacklist B, and a fault-resistant model zeta. Each gate beta that can be injected can be replaced by fault selection model G and construct a controllable faulty circuit. Thus, the fault resistance verification problem can be encoded as, for all primary inputs x1 to xk, fault control input C1 to CK, and fault select input B1 to BK. Maximum number of clock cycle when fault events can occur is less than or equal to NE, and the maximum number of fault events per clock cycle is less than or equal to NC. Meanwhile, the outputs of S and S prime differ at clock I. That infers the error flag will set to 1 before or at clock cycle I. This is the formal encoding of this problem. Here is an example. Consider an Xbox from rectangle cryptographic circuit with parity check, given the photoresistance model zeta with the maximum number of clock cycle when fault events can occur, and the maximum number of fault events per clock cycle can occur are equal to 1. Here is the encoding about this circuit. We also provide an acceleration techniques to improve verification efficiency. That is, if the output of this gate only connects to one gate and this gate can be injected, then it is seen to inject fault at the next gate. Thus, this gate does not need to verify. For example, here is the gate S5. Its output only connects to the gate S6, and we can inject fault at S5. So inject fault in S5 is same with S6. So S5 does not need to verify. We finally give the evaluation of our tools. We first compare the BDD-based tools to our SAT SMT-based tools. Each task was run with 24 hours timeout. In conclusion, our SAT-based tools farmer is able to verify fault resistance or 76 benchmarks, but the BDD-based tools favor runs out of time on 31 tasks. Here is a part of the result. We also give the evaluation of our gate reduction techniques. As the conclusion, our techniques was significantly enhance verification efficiency. Here is the part of our results. In future work, we are developing tools to automate the provision of countermeasure for cryptographic circuits. We also hope to apply this fault-resistant verification method to other scenarios, such as CPU. Additionally, further research on the joint verification of fault-resistant and other security properties is a particularly interesting topic. That's all my presentation. Thank you very much. If you have any questions, please feel free to contact us. We also look forward to more collaboration and communication with everyone.
Okay, let's thank the speaker, and hopefully we also have now someone online to answer any questions of the audience. There's no one online? Okay, so in that case, there's probably no chance to get answers to your questions. So yeah, if you have any questions, then please feel free to directly contact the authors. And this, yeah, brings us to the end of this session. There's a short track switching break in between, and then we will have the second fault resistance session right after the track switching break. Okay, so with this, let's thank all the speakers again, and then hopefully see you back for the second session.